All right, let's start. So I'll just do a quick recap of last class. Questions tak lang bolo. We started a new topic. It's called thermal physics. We're done with one subtopic. It's called thermal equilibrium. Thermal equilibrium is essentially when you have two objects in contact. Energy transfer will continue to take place, and the energy transfer takes place in both directions. But there's always a net energy transfer, and the net energy transfer is always from higher temperature to lower temperature, and it's called a temperature gradient. And the steeper the difference, like this is very high and this is very low, the faster the energy transfer takes place. And over time, what happens is the difference starts to get smaller and smaller. At one point, the difference is very small, so the differences in energy is also very little. So the transfer rate is going to be very slow because there are very few particles here capable of giving energy that way. So it takes time for their energy to go that way. And eventually what will happen is they will both have same temperature, which means their average kinetic energy is same, which means no more net energy transfer will take place. Energy transfer still takes place, but no more net energy transfer takes place. Also, very important to note that the energy is same, but the process stops when the temperature is equal. Okay, because thermal equilibrium. So what's the implication of this? Whenever you have two systems in contact, you need to wait. And you need to wait for the systems to transfer their energy. And once the energy transfer has taken place, it takes time. And eventually you'll realize the energy transfer has taken place when you notice that the temperatures become equal. Okay, so that's called thermal equilibrium. And we are starting this topic. This is very important for you guys. Things will get a little challenging. It's called internal energy. And I just briefly discussed it, so I'll just go through this one more time. So internal energy is a measure of the energy any material has. So any given object has an energy in them. And what's an indicator that they have energy in them? They have temperature. So if you look at any object around you, right, the temperature is not zero Kelvin. Like, for example, this room, everything is like 298 Kelvin, right? That's a lot of energy. 298 is 0 Tikhonik Bishi, right? So that means the table, the chair, everything around you, the molecules, they have energy. So the first thing we need to understand is what form is this energy? In what way is this energy within that, right? So it turns out for solids, liquids, and gases, this energy distribution is quite different. Okay, so we'll start with solid. So solid particles can only do one of two things. Either they're vibrating, or they're spinning, or they're vibrating and spinning. Okay, so it's a combination of vibrations and rotation. And turns out that vibrations are a form of Ke as well, because there's movement. Rotation is also a form of Ke. So let's say there's a top spinning very fast. It's not going anywhere, but it's spinning very fast. What does that tell you? It has Ke, right? It doesn't go anywhere, but it has energy in it due to movement, right? So vibration, rotation, all together is the energy that this material has. So if you want to find the energy in this material, what do you need to do? You need to find all the vibrational Ke, all the rotational Ke, and add them up, right? But there's another form of energy that we are ignoring here, which is the energy stored within the what of these atoms? Bonds, okay? And that is what you normally would refer as chemical potential energy. We just call it potential energy, okay? And there's a very easy way of picturing this energy. If you ever want to have a way of understanding what this is, try to imagine them as two molecules, atoms, right? And the bond in between them behaves very similar to a spring. So a spring stores what form of energy? Elastic potential energy. So if your particles here are moving close, the energy increases. Moving far, energy goes back to normal. Moving even further, energy again increases. Compressive potential energy, tensile potential energy, right? So the bonds actually behave the same way. In fact, there is a part in physics where, not in all A levels, later on, where you learn how the bond can be modeled as a spring, and chemical bonds actually have spring constants, which gives the material its elasticity. So that's why some materials are elastic on an overall level, right? That's because their bonds are more elastic in the micro level, okay? So yeah, you can imagine that. The only reason I brought it up right now is because the energy stored here is potential energy, right? So this potential energy is available in all the bonds that you have here. And I've just drawn a couple of lines here, but there's energy everywhere. So if eventually you want to find all the energy here, what should it be? The vibrations, the rotations, and also what? The potential energy that they store, right? You can harness this potential energy. How? By undergoing a chemical reaction. So when a chemical reaction undergoes, these bonds are broken, right? Or made, and in that process, energy is taken in or given out, right? That's where the energy comes from. So, whenever you burn something, oxygen and fuel mix to produce heat, right? That's these energies being released, like the enthalpy change, right? So anyways, that's the energy here. But that comes with a problem. Problem is, it's actually not possible for you to predict this. And I'll tell you why. If you think that this is rotating, this is vibrating, that is rotating, and you do your math, right? You will only be able to get the energy for that instant. But the problem is that these particles are not only vibrating all the time, not only rotating, they're doing a mix. So there's no way for you to be sure the amount of energy a material has at any given point. Why? Because the energies are random. And that's why you'll understand from lower classes that kinetic energy is a random distribution. So there's no fixed value. So there's no number I can set to my material. I have a gauge for it. What is it? Temperature. That my temperature is 20 degrees Celsius. I know this might have that much energy, but I can't say for sure. And we'll see later on, it becomes almost impossible, okay? So what we know is that this material has energy within it. The energy that it has within it is called the internal energy. And the internal energy is the sum of all the energies that you have inside, okay? Imagine all the energies, sum hoche internal. So what would the sum be? Your vibration, your rotation, plus what as well? Potential. Now, if you go to liquid form, things change a little bit. Why? Because now your particles are not only vibrating and rotating, they're doing this very kinetic energy heavy motion. What is it? Translation. They're going places, right? So they're going like from here, there, they're moving around. And as they move around, what happens is they also have K. And that's the new feature unlocked within liquids, where the particles actually go somewhere, right? Are they vibrating? Yes. There are particles still stuck within the structure. Are they rotating? Yes, inevitable. So eventually you'll find liquids will have vibration, rotation, translation, and also what? Potential. So potential is there everywhere. Okay, so far it might change. So that's liquid combination. So liquid can have, you probably say, the most diverse form of energy out there. Most diverse mane hocche all combinations. All combination possibles are there in liquid. Okay. But then comes the one that our chapter will be dealing with, and we'll be dealing with this in full detail. This will become a main theme. How does the energy combination look like in gases? Okay, so here's the thing. Gas particles are extremely far apart, okay, like really, really far apart. And the further you go, what happens to the strength of the bond between two particles? Does it get stronger or weaker? Weaker, right? So these particles are, like, mathematically speaking, infinitely far away. And they're so far away that this one's attraction on that is almost non-existent. Okay, that's first point. Secondly, the molecules in gaseous form are not bound with each other in a structure. So, free to move, random shape, random volume. So they're just moving around. And when they move around with insane amounts of K. We'll learn about this. Typical air molecules in this room right now, they have a speed of how much? Yeah, it's 500 to 700 meter per second. Average speed of every molecule hitting you right now, 500 to 700 meter per second, right? So they're going really fast. Are they spinning? Yes, possibly, right? Are they vibrating? Most likely not, right? But what physicists have done is they made an assumption, okay? Quite a, bold assumption, which is that they have assumed gases, right, don't have any potential energy. And then there's no energy within the bonds because we assume there's no bonds. Why? The particles are so far apart that the attraction of one molecule on another molecule is almost zero. It is not zero though, otherwise the thing wouldn't exist as a molecule or a gas, right? But we assume it to be zero. We also assume there's no vibration and no rotation. So for gases, we strictly believe that they only have what kind of energy? Translation K, ar kichu nai. So that means if I want to find the internal energy of this room, right, it's actually manageable. What do I need to find? The K of my molecules. I don't need to bother about whether they're vibrating. I don't need to bother about whether they're rotating. I don't even need to know if they have potential energy. So eventually we have a math at the end of the chapter. You need to find the total K of all the particles in this room right now. And it is doable. But it comes with the catch, obviously. Do all molecules travel with the same speed? No, right? So when you're finding that K, what K is that? Average K, and that's where you come full circle, because I think grade 9 start Coursera, that when you heat something, what increases? The average K. You get my point? So that's how we eventually wrap up the topic. So yeah, this is called internal energy. So internal energy is the sum of potential and kinetic energy. So there's a formula here. The symbol for internal energy is this, U. So U is internal energy. That is going to be equal to the sum of kinetic energy. Now, what kinetic energy? The sum of random K. Why random? Because kinetic energy can be of three types: rotational, vibrational, and translational. Plus, you have just potential energy in the structure. This is an equation that we'll be using to answer most of our questions in this topic. This one, okay? So internal energy is the sum of the K plus the potential energy that you have. The definitions and everything I've provided on the side. We'll go through that in a minute. So yeah, what is U here? U represents internal energy. Internal energy, yes, it is in joules. K যেটা এটাকে আমরা যখন অ্যান্সারে ওয়ার্ডসে লিখবো, we'll say random kinetic energy. And if you're wondering why random kinetic energy, because the kinetic energy is in different forms. What are the forms of K that we have? Rotational, vibrational, and the most energy hungry one, which comes in gases, translation. Translation means when the particle changes position. So I think you can take a guess, it's not there in solids. Solids are translational. And this one is just your potential energy that the particles have. Potential energy, chemical potential, but they prefer just potential energy. So yeah, that's the equation. So that's how you find what your internal energy of an object. Now, let me show you a couple of things before I'll give you a chance to write these things down. The definitions are here, okay? So let's say I have a plank of wood here, like a piece of wood, and I want to find the internal energy of this piece of wood. So let's say this is the wooden plank that we have, and at a room temperature, okay? And can you tell me what can I do to find the temperature of this wooden plank here? Temperature, no, sorry, internal energy. So what kind of energy does it possess to begin with? What's inside? Yeah, potential energy, correct. What else? Kinetic, right? Random kinetic. What are the random types of kinetic energy this wooden block might have? Vibration and rotation, right? So I want to know the total internal energy here. How can I find that? Ki korbo. Now, temperature, listen carefully, it's a little tricky. Temperature is a measure of what? Internal energy, right? But it doesn't tell you the total amount, though. And I'll give you a simple example of this, okay? This big table here is at 25 degrees Celsius, all right? And your book is at 25 degrees Celsius. Both of them have what temperature? Same, right? Do they have same energy in them? No. Like if you take every molecule in the book and find its energy, and you take every molecule in the table and find its energy, right? Will they both have the same amount of energy? No, definitely not. Which one has way more energy? The table, right? But they have same what though? Temperature, right? So the total internal energy is not really a direct representation of temperature. So it's not like I can use temperature to measure internal energy. Temperature is an indicator of increase or decrease in energy. So if I heat this up, let's say I take this plank here and I start to heat this up, one thing is definitely going to happen. What will increase? Temperature. And as temperature increases, what increases for it? The internal energy, right? But can you find out how much total energy it has? Impossible, okay? So if you're ever trying to find total internal energy of something, the answer is not possible. It is not possible, okay? And then even if you manage to figure it out, it won't be correct because it's an ever-changing form. Rotate হচ্ছে, vibrate হচ্ছে, right? So you can't really get the exact value. It keeps changing. However, তাহলে chapter to কোনো লাভ নেই because everything is just not possible here, right? However, we have something that is possible. You can actually find the change in internal energy. And this one you have done before. See, if I have this wooden plank here, how do I find out the increase in energy of this wooden plank? Does anyone remember any equation that helped us find that? Yes. Q equals to mc del T. Do you remember that formula, specific capacity? Yes, that Q, and I think now you'll probably realize they never wrote Q in your books. They never wrote Q in your question paper. It was always what? Del Q, because you were always finding the watt of energy change, not the absolute magnitude. Okay, so whenever we do our math, we are always finding changes in our syllabus, not the absolute value. Absolute value বের করা যাবে, খালি কার? Whose absolute value of internal energy can we find? Gases. And that's because gases just Ke থাকে, half mv square. Somehow you find the average velocity, you can find the total energy. But for anything else, it's not possible. Okay, so it is possible since we can calculate the change না, so আমাদের ideal gas নিয়ে কাজ করি আমরা, and ideal gas we make an assumption, and the assumption is that the gases don't have any bonds between them, they're just floating around, and it's something chemistry you probably will be introduced to. It's called the van der Waals forces. ওইটা হচ্ছে নাই in physics, so we assume that the gas molecules are not bound by that. So if they're not bound by that, right, they're just two individual particles floating around, there's no link between them. So that just energy data is just K, nothing else. Okay, it's an assumption, obviously. Right, so this is internal energy introduction. The definition that you have is here. I said to copy right now. So that's the definition of internal energy. It's a very common question in the chapter. Most of the questions start with that. Page 45. But if you have questions, let me know.
A-level grades depends where you're applying. So yeah, for where you need to have for application form, and then rest is actually an admission test. So no, so if you have like A and B in any combination, the rest is how well you do in your admission test. If you in fact, if you have plans to go into BUET or have aspirations, you should start studying right now for BUET, because the syllabus is very different, and then you'll probably find like 20% similar. And then once your syllabus ends, like A2, right? The admission test is in January, like end of the year. Yeah, so you have like 6 months, which is not enough. Average C. No, they have similar syllabus. So the syllabus in most private universities, they follow what BUET does. The only problem is that private universities have tri-semesters, like 3 semesters. So it's a very short time, and it's very difficult to cover syllabus properly. BUET has like 2 semesters, like bi-semesters, like semesters. So as a result, they can go more in depth. But the actual book, the content, everything's same. Huh? Yeah, I mean, they don't really teach anything. They, admission for admission test, you have to you just have to focus on math and analytics. This is analytical topic. That's the only one that you have to brush up before you go for your exam. That's very basic. No, I mean it depends whom you're asking. So my point is that I feel like English medium students don't suffer with the English. They struggle with the analytical part. No, there was Bangla in my time as well. You can opt out for it. So there's an option where you can just say that you'll give the exam in English, right? So sometimes if your luck is bad, they'll give you like a small writing task in Bangla, which happens like, once every 10 tests. In my one, I didn't have it. It was just a normal English test set. Yes, it's actually from like O-level, A-level standard. It was very easy. The only challenge is speed, like speed, how fast you can do it. So the time is the constraint, and you're not allowed a calculator. So these are the only constraints. But the math is not difficult. No, at least in my time we didn't have calculators allowed, so no calculator. But the maths are designed that you don't need calculators. Like the numbers are all proper fractions and proper decimals and everything like that. So hindsight, I think it would have been helpful because I did it myself most of the time, but I found this very useful book. So I just did that book. It was a GRE book. It's like another test. So if you can, ace GRE, then the IBA test wouldn't be a problem. Yeah, that's something that I was curious about. So normally when you get admitted, they'll give you a list, and that's based on merit. Yeah. I don't know actually because my roll number was the last. No, however, I later on asked, they said that they don't publish that. So the rolls are based on when you take your admission. Yeah, so, but in Dhaka University or BUET, for example, that list is very important. Yeah, because that will let you choose what course you want. You get your preference. Oh, the interview is the worst. They just, I don't know if you've seen like reality shows where they interview you and they try to bring you down. They basically follow their handbook. So they'll ask you the like most randomest question. They'll try to make you nervous and make you lose your confidence. You just have to hold your ground. Sometimes students will try to be overconfident. That's also harmful. So the balance is very risky. No. For me, they just ask you what's your aspiration, and then the first question they ask you is like, why from science to business? That's the first question they ask you. So you just say that science builds your analytical mindset, which will be helpful in business. So it's like the same question, same answer all the time. Because eventually you want to go into finance, right? You need strong math background. So an engineering student does similar math in finance. So that's why you need that background, right? If I just did like, commerce and business studies, no offense to that, but it wouldn't be possible. A test take apart. The test is math based, right? So that's why you just have to say that. And then now they know that students memorize the typical questions. So they'll ask you the most random thing out there, like what's the first headline in newspaper today? And then you'll be like, oh, I don't read newspaper. And then the conversation starts from there, like, why not? Yeah, and then the interview board is very strange. So you sit in the center and there are people all around you. And sometimes questions come from the back, right? And, I was wanting to look at them because it's disrespectful not to look at them. But then do you turn around and stop looking at them? Because these are like the main people who are interviewing you. So yeah, it's something like that. Average B, like A, B. 2 A's and a B. To qualify for the admission test. No, ওটা খালি medical. Yeah, medical, you're like everything together adds up, but not for engineering or business. Absolutely, no, nothing. You need a high school certificate, but they don't care how well you did. Okay, go to page 46. এখানে হচ্ছে we'll look into the ways of increasing the energy. Okay, shall I screen it? Let's do this. Let's say you have a metal block here, and we want to raise this internal energy. So kemne energy বাড়ানো যায়, that's something that we need to learn. Okay, so you have a metal block, and you want to raise this U value, internal energy. So for internal energy to be increased, what are the different ways you can do that? So I'll put it in a simple way for you. How can you increase the temperature of a metal block? Tell me all the ways you know. Yeah, so you provide heat. What is heating? What is the process of heating? Like, what does it actually do? Yeah. But heating যেটা হয় ওটা বলি কি হয়, you basically take an object and you put it on a flame. The flame has greater internal energy than your object, and that's like typical flames at 200-400 degrees Celsius. So when you place your object there, isn't there a temperature gradient? So what happens? Energy transfer takes place. So it's basically energy transfer by means of conduction from an object of what temperature? High to low. This is called heating. Okay, ভালো, এটা করা যায়. It's the most common way of doing it. Well, what are the other ways? So you said hammering. Why would hammering give energy? Because the particles okay, yes, that's correct answer. So one other way of providing energy, so I'll give you all the ways here. So first and foremost is the one that we just discussed, heat provide kora, very tried and tested active process. So you just place something hot here, and because the other object is higher temperature, energy transfer will take place from high to low. So that's very straightforward process. Okay, but what about hammering? So when you hammer something, why is there energy increase? The reason behind that is, if you see in microscopic levels, right, you'll find that there's actually deformation taking place, like the objects are getting distorted in the molecular level. And once you do that, what you're doing is you're breaking some bonds out there. You're distorting their position, and there's a change in displacement here, X. And what are you applying here? F. So what are you actually doing on the object when you hammer it? Work. Okay, so work is done on the object. The work done is going to be the force you apply into the amount of deformation that takes place. Typically, deformation is very limited. That's why you don't really see a temperature rise right away. But if you keep hammering for long enough, right, wouldn't the deformation start to stack up? And at one point, it will actually get warmer because there's energy there. Now, what if you deform it with one go a lot, right? It'll heat up right away. And there's actually a mechanism like that. I don't know if you know how igloos are made. Igloo, like ice use kara hoy. So if you take two pieces of ice, right, and you pressurize them a lot, do you know they stick? They'll just stick like they're like cement. They can't come back anymore. Why? Because when you pressurize them a lot, right, you're giving energy, you're doing work. What happens in the gap is that the water melts, and the water melts and instantly freezes. So what happens is it becomes one object. So if they make igloos using that, you'll notice the igloo is like a dome shape, right? But the things are not falling down because of the ice used for it, and they pressurize the two objects together to increase the temperature, and that causes the ice to melt. A liquid is formed. The liquid instantly freeze with it and binds two objects together. Okay, so yeah, hammering is a good option. So this is deformation. Anything else? Yes, that's actually a very good method. So what you do is you pass what through this material? Current. And as you pass current through the material heats up. Classic actor scenario. Can anyone tell me why passing current through a metal causes it to heat up? Positive lattice ions, right? So the electrons that are flowing through, they have energy, and they're not having a free time to pass through. They're colliding with other ions out there. Every time they collide with the ions, what do they transfer? Energy, right? And that energy transfer eventually raises the temperature. And that's the reason why whenever current passes through anything, what do? They heat up. So yeah, you have deformation, you have passage of current, you have heat provided here. Yeah, so artoche friction, that's actually true. So I can take this block and move it on a surface and it'll start to heat up as well. Friction is very common, like the process of heating up, right? What's happening there? So like, why does it heat up? The collide with the ground, and why does it heat up? Acha. So এটা আমি বলি কি হয়? So once you start to move one way, there's friction acting on you, right? The friction is microscopic level at two surfaces colliding with each other. There's force being exerted, and the object covers distance, right? So eventually, friction is nothing but actually what been done on the object, work, okay? Work done by the imperfections. মানে তোমার যে মেটেরিয়ালের মধ্যে হচ্ছে by the rough surface. So this is work done. Right, so this is work done. This is also work done. Turns out current out chilo, I forgot to mention. Current is also work done. What kind of work is done when current passes? It's called electrical work done, okay? Work done by the supply. Or no way, just try to improvise. Tell me different ways in which you can heat your object. So you have friction, you have deformation, you have current, you have heat. Are kichu? Yes, very good answer. We have it in our syllabus, but do you know what that is? So there's a coil with an alternating current in it, and you place like a metal inside it, it will start to melt. All right. So what is causing the melting process?
So the magnetic flux constantly changes within the substance.
And the substance causes the magnetic field lines. And what is induced in it?
Magnetic field.
In the coil, in the metal.
The substance itself, right? So the flux actually changing the surface, causing a collision inside.
Acha. Very close, but the answer is that when there's a coil inside a metal inside the coil, and the coil has change in current, there's a change in magnetic field, right? Which is cut by that metal. And because the metal cuts the magnetic field lines, there's EMF induced in it. It's called Faraday's law of electromagnetic induction. Yeah, and that causes what to flow in that material. Yeah, and the current is eventually the answer. So the heating effect that you see is because that small piece has extreme amounts of current passing through it. And this only works if you use a metal. So if you use a non-metal, it doesn't work because there's no current flow possible. Okay, so eventually it's current. Architecture? No. air resistance, air resistance is also true. Like asteroid falling into the Earth's atmosphere, right? Doesn't it heat up? Why? Again, it's doing what? Work, right? So yeah, I'm actually trying to get to a point. The point is, that wouldn't heat it up. Releasing it would. Okay, because that's when the work is done against gravity and dropping it, right? Okay, so let's get to the point. So if you want to increase the internal energy of something, right? There are only two ways out there. You may come up with other ways, I believe, but there are actually just only two ways. The two ways are summarized ways. You can either do this, একটু carefully দেখো কি হচ্ছে. You can either do this or you can do that. What are these? So Q is the official symbol from now onwards for what? Heat. So you can only heat and make an object raise its temperature, or you can do W. W is what? Work. Eçhara, it is universally impossible for you to raise temperature of anything. It's just by heating and by doing work. And if you look at all the examples we have done here, these are all different types of what? Work being done. Okay. So if you ever want to increase the temperature, there are only two possible ways in the entire universe. It's only either you provide heat or you do work on the system. Like a gas, for example. If you compress a gas, does it heat up or cool down? To compress a gas, heat up, right? Do you know why? Yeah, so এটা তোমাদের কিন্তু এসে ছিল. I don't know if you can recall. Gases এর জন্য work done একটা formula ছিল. কি ছিল মনে আছে কারো? Yes, exactly. Work done equals to P times del V. Okay. This was the formula for work done on gases, and yes, this would cause the gas to what? Heat up, right? So yeah, this is what you need to know, that there are only three ways or two ways in which you can increase the internal energy of a material. It's either by doing work or by doing or providing heat, and that is where it just heads up there, Rakhi. It's called the first law of thermodynamics. First law of thermodynamics. As it turns out, the first law is actually the second law of thermodynamics. Do you know why? Because there is actually something called the zeroth law of thermodynamics. So it starts with zero. And the reason behind that was we first came with the first law, and then we realized that there's actually a much more fundamental law that governs thermodynamics, more basic than the first law itself. And by the time we realized this, the other laws are already there. So we gave it the name the zeroth law. The zeroth law of thermodynamics is the law of conservation of energy. The energy can neither be created nor be destroyed. It goes from one state to the other. Isn't that the first and fundamental thing that governs everything? So like a zero. Right? This is the first law. Second law, I think physics and I, thankfully, because it's very complicated. Chemistry, you have a bit of it, I think. Entropy. So do you have it in AS or A2? A2. Yeah, so entropy is the second law of thermodynamics. Okay, we don't have that in physics. So we didn't have the first law. First law, key state kore, the change in internal energy of a material is equal to the change provided due to heat. So plus the change due to work done. So I'm partial steps like the different ways you can increase energy, but yeah, this is the law that we have. First law. Second law is not part of first syllabus. 3. Zeroth, first, second. Okay, so edit a copy kernel to increase the internal energy of material. Yeah, there's a gap there. These are the following ways. So work done হচ্ছে দুই টাইপের থেকে মেকানিক্যাল ওয়ার্ক Charging is discussed correctly. You had briefly about this in your O levels, which is when you heat something, right? Does the temperature increase? Always. Yes, right? I mean, if you're heating something, temperature should always increase. There's an exception though. What is it? Yeah, when it melts and when it boils, it's called a latent heat of fusion and vaporization. তখন কি হয়? You're providing energy, right? Why is it the temperature not changing?
So the energy is being absorbed to like break the forces in the body.
Right. So the energy is taken in, but then why doesn't the temperature change? No, I understand. So but the object is consuming the energy I'm given, right? Why doesn't the temperature reflect that?
So like the energy is being released for bond breaking and like the energy that's being absorbed for like breaking the bonds that cancel each other out. And energy changes it.
Right. So turns out that energy, right? Indicator of kinetic energy is temperature, but indicator of energy is not temperature. And which kind of energy is not indicated by temperature change? Potential. So if there's an object's potential energy changing, right, you wouldn't see any reflection of that in the temperature. Temperature is a direct indicator of which energy only? Kinetic energy. And when a material changes state, the K remains what? Constant. Because the energy is now used to break the bonds. So the particles don't gain any K, their speed doesn't change. Once that process ends, they again start to speed up. Okay. So intra energy change is due to changes directly proportional. So the energy entropy goes to split the particles apart. So nothing goes to their actual movement.
Right, so next class, we'll work on this equation. This equation is a chapter on its own. Just call this first law of thermodynamics.
Twenty-five percent similar. Chapters are similar, but the way they ask questions is more like how we do the questions. So they have calculus and complicated math in physics. That's why you have to know that. But if you study, I mean, if you can tackle Cambridge physics, you can easily tackle that as well. It's just that since you have no clue what it is, you don't have a preparation. Content similar. মানে চ্যাপ্টার গুলোর নাম দেখবা সব সেম, বাট কোয়েশ্চেন করতে গেলে দেখবা যে it's different. No, difficult. It's question গুলো just unnecessarily complicated.